Daisy, morning. Morning, Daisy. Did you send the money? Morning, guys. Since we finished the other section of normal distribution, I want us to share elasticity. If time allows, also we shall have to look at simple harmonic motion. People ask me to do that, but I can't look at simple harmonic motion before people confirm elasticity. So elasticity is basically a concept which requires, one, extension of items, as long as that item is an elastic material. So if the item is an elastic material, it can experience what we call elasticity. And in that regard, for example, if you consider a string having original length AB, and this original length is small l, when we pull it further to a new position B prime, then it will extend with an extension E away. Some books have it as X away. Others have it as delta L. All those imply an extension being in place. Or it occurs extension has taken, it means extension has taken place. So with that regard, the distance we have here can be what we call our new length, L prime. So extension would be the new length you have now, L prime, minus the original length. Sometimes also this original length, some books call it L naught. So it can be L prime minus L naught. So this will give you our extension, which is XO, which is delta L, depending on the book you're using. So one should be in position to know that. So it is from here that we have what we call Hooke's law. Hooke's law states that force is directly proportional to the extension produced in an elastic material provided the elastic limit is not exceeded. The reverse can be true. One can also state it in a way that you can say that the extension produced in an elastic material is directly proportional to the force applied the material. It's directly proportional to the force applied, provided the elastic limit is not exceeded. So if someone gets to know that, then from Hooke's law, force we are saying is directly proportional to extension, or force is directly proportional to the displacement, x. Okay? So if someone gets to know that, then force is going to be equal to a constant times extension when you remove the proportionate sign. If you're using x, it will be equal to force is kx, where this k is going to be called, where k is what we call the modulus, okay, the proportionality constant, which is defined by lambda over the original length, which is modulus of elasticity of the material out of the original length. So in this regard, always k is lambda over L naught. So we can say force is equal to lambda over L naught times x. Or we can say force is equal to lambda over L naught times E. Of course, knowing very well that lambda is the modulus of elasticity and L naught is the original length of the material before extension. Modulus of elasticity is measured in, the SI units for it are newtons. They are newtons because the distance cancels in meters, so it will have newtons. So basically, that is the general illustration of how elasticity will be taking place or will be looked at. But most importantly, it has what we call the modulus of elasticity. It has what we call the original length. It has the extension. Then it has the force that has been applied. If it's a string, then force in the string is tension, capital T. So in strings, tension is equal to lambda over L naught times x. Or tension is equal to lambda E over L naught. Then furthermore, we also have what we call energy stored in an elastic string. Energy stored in an elastic string or spring or material. Now, you will see that as we do work from B to B prime, we are moving a distance small x or small l. So what happens is, if this was the original length, L naught, then we are going to do some work to extend it to some point. And this work we are doing has an extension E. So x is actually E at that instant. Now what happens is, the small work we do, the small work done, is going to be equal to force in the spring times the small distance we are going to extend the spring or the string. With that regard, to get the total work done, you integrate on both sides. From no work to some work done is equal to the integral from no extension at all to an extension x of f dx, whereby total work done shall be equal to the integral of f dx from 0 to x. Some books can have from 0 to e. This will give me integral of lambda over L naught times x dx. And this is integrating from 0 up to x. So when you integrate this, we shall have lambda x squared over 2 L naught from 0 to x. Therefore, the total work done will become lambda x squared over 2L naught. If you're not using X and you're using E, then energy stored or work done shall be equal to lambda E squared out of 2L naught. So this is how we can get the energy stored in an elastic what? String or spring. So with those definitions, we can now go ahead and look at an example of how this can be handled. So we shall have example 1. Example 1. Unless, before I go to example 1, is there anyone who have the challenge in the definitions I've reminded you of? Any concern in these definitions I've mentioned? So if no concern, question 1, an elastic string. An elastic strip of natural length. So L naught can also be called what? Natural length or the original length. Of natural length, 0.6 meters is stretched. Through 8 centimeters by a weight Someone was trying to mute me out. Sorry, let me start with the example straight away. So I was saying example 1. An elastic strip of natural length (0.6 meters) is stretched through 8 centimeters by a weight of 1 kilogram hanging on it. Find the tension in the string when the total length is 72 centimeters. So to start with, perhaps this strip was hanging vertically by a weight of 1 G newtons. Then the tension in this case was, because it's not moving up or down, tension is equal to 1 G Newton. The formula for tension is going to be equal to lambda, natural length, my modulus, over natural length, times the extension, x. So for case 1, the original length was 0.6 meters. Then it was stretched through 8 centimeters, meaning the extension, which is x, is 0.08 meters. So this first information helps us to find the modulus of elasticity of the string. So we shall have the tension, which is 1G, is equal to lambda over original length 0.6 times 0.08. With this, lambda is equal to 9.8 times 0.6 out of 0.08. Can we find lambda using a calculator? Someone give me the answer. What is lambda? Lambda is
73.5.
73.5 newtons. Now, furthermore, the question said find the tension in the strip when the total length is 75. So new length is 75 centimeters. Original length was 60 centimeters. So in this case, the new extension shall be 75 minus 60, giving us 15 centimeters. So our new length, our new extension is 0.1 what? 15 meters. Sorry, they said it was 70 to 75. It was 72. Making this 12. If this has been made 12, then we shall have 12 centimeters, which is 0.12 meters. Now they're asking for the tension when we have such an extension. So the new tension shall be lambda out of the original length times the new extension. Or one can write it as lambda of original length times x prime. So the new tension among the least things I expected today is network, because I'm in the middle of the city. I don't know why I'm getting this challenge. But let's finalize that part. It was going to be lambda of original length of E prime, which modulus was 73.5 divided by the original length, which was 0.6, times the extension, which is 0.12. Can we compute with a calc? Here it goes there 5 times. Calculator, what do we get? Someone compute with a calc, what do we have?
14.7.
14.7 newtons. So with that, you can now find the tension if you can predict the modulus and if you can predict the extension. So basically, you see that that is the most important thing. One, you should know the tension, modulus of elasticity. You should know how to find the extension produced. Yeah. So if I write case 2, have that down, and I have case 2. So we have a light elastic string of natural length 2a is fixed at one end A and it carries a mass of 3m at the other end. When the particle is hanging free, a horizontal force of 3 mg newtons is applied to it when the particle is in equilibrium, the string is inclined to the vertical at an angle alpha, and the extension of the string is A. 1, find the value of alpha. Then 2, show that the modulus of elasticity of the string is 6 mg root over 2 newtons. So you can have the question down. A light elastic string of natural length 2a is fixed at one end A, and it carries a mass of 3m at the other end. When the particle is hanging free, a horizontal force of 3 mg is applied to it. When the particle is in equilibrium, the string is inclined at an angle of alpha to the vertical, and the extension is small a. Find the value of alpha and then show that the modulus of elasticity is given by that one. So to start with, the string has been pulled some side by a horizontal force of 3 mg. There is a particle hanging on it downwards. This particle has a mass 3m. When you attach weight, it becomes 3 mg also. Now there is tension here in the string. We don't know. But firstly, we have an angle alpha inclined there. Also, this angle here will be alpha. So with this, we can carry out the procedure to find tension first. Because to find the modulus, you need to have tension. Now we shall find tension using either resolving or Lami's theorem. So the shortcut here is Lami. If I use Lami, it will look like this. This will be 90. This is 3 mg. This also is 3 mg. Then this angle right here is 90 plus alpha. Then this one is going to be 180 minus alpha, because you remove only this part from this vertical straight line. What does Lami's theorem state? It states that sine 180 minus alpha over the force opposite to that angle is this one. 3 mg is equal to sine of 90 out of the force opposite to this angle is the tension T, is equal to sine of 90 plus alpha out of the force opposite to it is also 3m what? G. But sine of 180 minus plus alpha, but sine of, you must be trig machines by now, is equal to sine alpha. Then sine of 90 plus alpha is equal to what? The best way to interpret this is by using an example of obvious angles like 30. You say alpha is 30, when you add 30 there, you get 120. Sine of 120 is 0.866, which is the same as cos of 30. So this will give you cos of what? Alpha. If you don't recall that, go back to trigonometry backhouse 1. So this is sine alpha over 3 mg is equal to sine of 90 over tension is equal to cos alpha over 3 mg. To start with, I can deal with these two. You see these two here? Because we don't have anything which has the entire solution, so I can deal with these two and have sine alpha over 3 mg is equal to cos alpha over 3 mg. These two can divide off, and we shall have tan alpha is equal to 1. So when you confirm that tan of alpha is 1, then alpha is 45 degrees. So having confirmed that alpha is 45 degrees, I can substitute back here. Sine of 90 is 1 over the tension shall give me sine of alpha over 3 mg. But sine of alpha is sine of 45 over 3 mg. So when I cross multiply, the tension will become 3 mg over sine 45. But sine 45 is 1 over root 2. So this is 1 over root of what? 2. So finally, tension will give me 3 mg over root 2 newtons. So find the value of alpha, we have found it. Show that the modulus of elasticity is that. But I told you modulus, you first need to find tension. So having gotten the tension, we shall recall that tension is got from lambda over natural length times x. But the statement in the question says x is actually equal to a. So if x is a, then our tension is 3 mg of root 2 is equal to lambda over the original length was what? The original length or the natural length was 2a. So divided by 2a times small a. I can divide the a's, and finally I cross multiply lambda to give me 6 root 2 of mg newtons. And hence I would have got the modulus of elasticity. Now, what if someone says, but teacher, me, I'm not comfortable with the Lamy. How can I find the tension using the resolving techniques? Those of us who recall resolving, you can resolve t to the vertical and have t cos alpha, t to the horizontal and have t sine alpha. So horizontally, you will have t sine alpha is equal to 3 mg. Vertically, you will have t cos alpha is equal to 3 mg. This becomes equation 1, this becomes equation 2. When I divide Roman 1 by Roman 2, I'll get t sine alpha over t cos alpha is equal to 3 mg over 3 mg. This one still will divide off to give you 1. I divide the tension. Finally, I'll go back to the same thing, giving me tan alpha as 1. Hence, still alpha would be 45 degrees. So that's why I was saying one can go for resolving or one can use Lamy. Remember, Lamy's theorem is a theorem which only looks at 3 forces in equilibrium. When those 3 forces are in equilibrium, we can be in position to apply Lamy's theorem and solve for whatever unknown is missing in the statement. So any question on such an illustration? So we can have that down. Then afterwards, I'm going to have another kind of illustration which will combine two strings. Then we shall go for numbers which have energy. Now, those who are offering physics, this is an advantage because you also cover elasticity in physics. So, and if you understand very well elasticity of mathematics, mechanics, it is also pretty easier to interpret elasticity of physics. So let me know when you're done to download, please, so that you can move on to the next one. Any concerns there? Example 3.
Excuse me, teacher.
Yes, please. Should I go back?
You first go back a bit.
Okay. Yes.
Okay, I'm done.
Strings SC and BC are both of natural length. Are both of natural length 5L. SC is inelastic. When they say inelastic, means it doesn't extend. While BC has a modulus of elasticity lambda. A and B are attached to 2 points in a horizontal line. Distant 5L apart. A mass m kilograms is attached to C. And the system is in equilibrium. In a vertical plane with the BC of length, 6L. Find the value of lambda. Find the value of lambda. Hence, show that the tensions in the strings CA and CB are 3/4 mg and 7/20 mg, respectively. So we have strings A, B, AC, and BC are both of natural length 5L. So our AC is an elastic, while BC has a modulus of elasticity lambda. When they tell you the other one has a modulus, it implies that it is elastic. So with that regard, you will find that so they are jointed. These strings are joined at C. So if they are joined at C, this is how they are joined. So they are joined at C. This is where C is. And at C, they have put a mass of mass M, giving me mg. AC can have tension T1, then CB can have tension T2. All right. So with this, you'll find that the distance of separation here was 5L between the horizontal point where they were connected. Now, originally they were of the same length, but you cannot just say they're of the same length and then assume the angles here are the same. The angles are going to be different. Do you know why? It's because one of them is extending and the other is not. So this angle here is alpha. This one here is theta. Why is it so? It's because CB has extended while AC has not extended. Right? Now this one is, for example, was 5L. Now they said the system is equivalent with the BC of length 6L. Now the length of this one has become 6L. But it was originally also 5L. So the extension shall be 6L minus 5L. So the extension is actually what? L. So if the extension is L, first of all, we can find these angles. One, I can find theta, whereby I can use A squared is equal to B squared plus C squared minus 2BC cos angle opposite to A. So I'll use 6L squared is equal to 5L squared plus another 5L squared minus 50L squared cos of theta. Where does the 50 come from? The 50 has come from 5 times 5 times 2. But there are 5 L's, so it becomes 25L squared times 2. Then this one also gives me 25L squared, giving me 50 squared. So 36L squared is equal to 50L squared into 1 minus cos theta. So when I divide, I'll have 1 minus cos theta is equal to 36L squared over 50L squared. So I'll get cos theta as equal to 1 minus 36 over 50, giving me what? 14 over 50, which is the same as 7 over 25. So cos theta is equal to 7 out of 25. If I get that, consequently, I can find sine theta. This is 7, this is 25. This will be root of 25 squared minus 7 squared, which is 24. Because it comes from 625 minus 49, you get 576. Confirm with the calculator. We get that result. So this is what? Our theta. So you can deduce sine theta as 24 over 25. We can also get angle alpha. Alpha, I'll use 5L is equal to 6L squared plus 5L squared minus 60L squared cos alpha. How does the 60 come about? It is 5 times 6 times 2. So with that, gives me this is 55. I mean, this is 61. This is 25 L squared. 60 L squared cos alpha is equal to 61 L squared minus 25 L squared. Or one can subtract from this very line. So cos of alpha shall give me 36 L squared out of 60 L squared. By 6 you get 6, by 6 you get 10. Here you get 3, here you get 5. So cos alpha is 3 over 5. When you design a right angle triangle, you can see that cos alpha shall be 3, this will be 5, this will be 4. So having gotten the angles, we are ready to resolve. The first question says, find the value of lambda. If you use lambda right here, we can also find this angle beta. So one can use lambda using beta, using 90 plus alpha, using 90 plus theta. So that sine of 90 plus theta over T2 is equal to sine of 90 plus alpha over T1 is equal to sine beta over mg. Can we try to find out what alpha is? Let's find out these angles. Give me theta. What is theta? What is alpha? Then also deduce for me beta. Beta comes from 180 minus theta plus alpha. Firstly, what is theta?
73.7.
73.7. Then alpha?
53.1.
53 point?
1.
Even beta is 53.1, I guess. So this 53.1 plus 73.7 minus 180. Subtract it from 180. What do you get? You get the same? (53.1 plus 73.7), 180 minus that answer. You must be getting 53.1. Is that right? You get the same answer?
6.2.
What do you get? We get 53.1, not so. Oh, if you want to see it,
It's 0.2.
okay, are you sure? 0.2. But the idea I wanted to get out of here is this. Beta, if you consider beta, you'll have 5L squared. I mean, yeah, you'll have 5L squared is equal to 5L squared plus 6L squared minus 25L 6L cos of beta. It will be the same statement like this one. And by induction, it means alpha and beta are the what? Are the same. So if alpha and beta are the same, we can be in position to deduce and say this is cos theta over T2 is equal to cos alpha over T1 is equal to sine alpha over mg. Which sine alpha I've already attained here, I can get it from this triangle. Since I'm looking for lambda, lambda is in T2. So I'll have cos theta over T2 is equal to sine alpha over mg. So we can get cos theta is 7 over 25 over T.
Excuse me, teacher.
Yes, please.
I feel we made a mistake
Where?
for the alpha part. Then it's one 6L and one 5L. They're not both 6L.
There is what?
Remember, like according to the diagram, one is supposed to be 6L, then it's supposed
Yes,
to be
this one is
5L
6.
squared is equals to.
When I'm finding what? Alpha. When I'm finding alpha, when I'm finding theta. Hello?
Oh, I think that's it.
I think it's right, huh?
Yes.
Yeah, it's okay. Okay. So can I substitute for sine alpha? Sine alpha is 4 over 5 over mg. So T2 shall be mg times 7 over 25 times 5 over 4. Here once, here 5. So T2 shall be 7 mg out of 20 newtons. Having gotten tension, remember tension is defined by lambda over original length times the extension. Now I can make the extension produced we saw was L. So we shall have 7 mg out of 20 is lambda over the original length. The original length was what? 5L times L. I can vamoosh the L. I divide the 5 once by 5 here 4. Thus, lambda shall give me 7 mg over 4 newtons. So that is our value of what? Of lambda. So having gotten lambda, they said, show that the tensions in the strings, actually we have already got the tension 1 here, tension T2. We are left with only tension T1. So T1, use this one, cos alpha over T1 is equal to sine alpha over mg. Cos alpha is 3 over 5 over T1 is equal to 4 over 5 over mg. When I divide by 5, I'll get T1 is equal to 3 mg over 4 newtons. Hence proof. So you've confirmed already T2 is this, which is in the question as the proof. We have also proved what this one is. So that's what our number was requiring, unless if someone has a challenge. Then others who wanted not to use Lamy, you can resolve from here. So that you have T2 cos alpha, you have T1 cos theta. Then you equate the horizontals, then you also resolve to the vertical. If you resolve to the vertical, you'll be in position to have, if you resolve to the vertical, you'll be in position to have what? You'll be in position to have, vertically when you resolve, you'll have T1 sine theta. Then also vertically you have T2 sine alpha. Then these two, you add them together. They would be equal to the weight mg. So you can download. So those of us who are not interested in Lamy, you go for resolving. We'll come up with the same answer. So have that down, then we look at examples in work done. So with this work done, we shall have to see that you can do some work in stretching a material from a point 1 to another point 2. And the difference in the work done is the difference in the energy stored. But the work done in an elastic spring is stored as, or work done is done and is stored as energy. But the energy in the elastic string is called the elastic potential energy. Hello? Hello? Tell me class. Thank God. Nagambye yawe mtwale binja gikola gwe. Kale mweka 5. Bino byonna byagenda oyo okukwira bino eddagala kale ngenda kuweereza. Okay, so I trust that you must be done by now. Can we have the next example on work done in an elastic string? That is elastic potential energy, as I've termed it.
Yes.
Yes, teacher.
Okay. Work done. In an elastic string is stored as elastic potential energy. We call it EPE. So, work done in stretching a material from X is E1 to X is E2 shall be, or is given by, work done shall be lambda over original length of E1. The longest is E2 of E2 squared minus lambda over original length of E1 squared. This will give us lambda over L naught of E2 squared minus E1 squared. We should also note that something might have extended, but then we stretch it further from a given extension to another extension. The work we do is the difference in the energies stored when extending those two items. Why is it called elastic potential energy? You know, when the force which is stretching it is removed, the material retains its original shape or size, or it goes back its original length. The only reason it goes back to that original length is because it has energy stored in it as elastic potential energy. So it is that energy which takes it back to its original standard or shape. So an example. An elastic string of natural length (0.3 meters) is stretched through 4 centimeters by a 1 kilogram weight. hanging on it. Find the work done. Find the work done. Find the work done in stretching. Find the work done in stretching the string from a length of 0.35 meters to 0.42 meters. So to start with, they never gave us the modulus of elasticity. And according to this, we have a material which first extended up to here, then it was extended further. The first extension has a distance E1. Then the second extension has a distance of extension which is E2. Now it has a tension in the string, which can be the force in the string, and the weight of the body is 1 kilogram, which is 1 G-Newton. So from F, or from tension is lambda, over original length times extension, in the first case, they say it was stretched through 4 centimeters. So E is equal to 4 centimeters, which is 0.04 meters. So tension would be lambda, which we don't know, times 0.04 divided by the original length, which was 0.3 meters. But because it is at equilibrium, the sum of upward forces is equal to sum of downward forces. And with that regard, the tension is equal to 1 G-Newton. So 1 G-Newtons is equal to 0.04 lambda over 0.3. With this, you can confirm lambda as 0.3 times 9.8 divided by 0.04. Calculator, what is lambda? Hey, I forgot something on the work done here. There was a 2 down. So what is the value of lambda? In actual sense, this is the same as 3 times 98 over 4. What do you get? What do we attain? When you compute that with your calculator,
73.5.
73.5.
20.5.
Newtons. Then we can also have to attempt what the part 2 calls for. Part 2 says, find the work done in stretching the string from a length of 0.35. So for 0.35, the extension produced here is 0.35 minus 0.3. The extension E1 is 0.05. Then for 0.42, we get a second extension, which shall be 0.42 minus 0.3. The second extension is 0.12. So the work done in stretching, guys, first hold on. kale. Njagala kukubirako about how you connect cameras on the farm. Kale. Okay, sorry for that. I had to say hello to this long-time friend of mine, and yet I need him somehow, somewhere. But anyway, it's okay now. Okay, we shall have work done shall be. Work done is defined by lambda over 2 lambda naught of extension E2 squared minus E1 squared. With this, we have got natural length as, lambda as 73.5 divided by twice. Natural length was 0.3 into brackets 0.12 squared minus 0.05 squared, close brackets. Calculator, can you give us the answer? Give me the answer as I write down the last number. So what else have you got?
One 1.4578.
1.4.
578
joules. Correct. So you can have that down and then have this last example. We need to make it snappy. You never know, the biology teacher might sign us out. Or I should leave you and you try it out. So hurry up and we try out another number for time elapses. So in that case, you'll see that one, you have the lambda, you have the modulus of elasticity, you have the energy given, you have, but you don't have the extension yet. So the first concern is to find the extension itself. From the formula of energy, which is equal to lambda over L naught times 2 of E squared. The original length is 2 meters. Then the modulus of elasticity is 60. then the energy is 0.9375 joules. With that, we can substitute and make E the subject. 0.9375 is equal to 60 over 2 times 2 times E squared. Then you can make E the subject by making the square root of 0.9375 times 4 out of 60. Calculator, you can compute and get the answer. When you press the calc, what do you get?
0.25.
0.25 meters. Then the last question says magnitude of the deforming force. Let me not go to the next page. Let me use this part here. Force is got from lambda over original length times extension. So force shall be 60 out of 2 times the extension, which is 0.25. By 2 once, by 2, 30. 30 times a quarter to give us 30 over 4, which is equal to 7.5 newtons. So with that, we have discussed what we call elasticity and Hooke's law. So allow me send you some numbers for you to handle and try out. Then on Friday, I would like to discuss simple harmonic motion because it would be easier to have, because simple harmonic motion has some concept of elastic items, elastic strings and springs. So it's better to first get the knowledge of elasticity. So on Friday, we come for simple harmonic motion of mechanics mathematics. Okay? Unless if someone has a question, but if no question, I think we can call it a day. So download that and finalize, then we go for the next lesson. Hello? I'm okay, sir. How are you? Hello? Yes, sir. In Nabisho, sir.